from UC Irvine, and Professor Robert got his bachelor degree and master degree from Johns Hopkins, and then a PhD degree from MIT. Now he's a professor at the UC Irvine, and he is also a director of founding director of the Materials Discovery and Synthesis Center at UC Irvine. And his research mainly focused on the structure property relationship of nanomaterials, and he fabricated materials, tested materials, and also ran modeling and simulation of those materials. And due to his achievements, he has earned numerous awards. That includes NSF Career Award, DOE Early Career Award, and Army Research Office Young Investigator Award, and many more. Okay, so to have this online, you can read. Okay? I have to spend not 10 minutes to read all of the awards, so probably you need to read it. And today he's going to share his recent research perspective about manipulating defects to improve the mechanical property of the materials.
Great. Hey everyone. If we're chatting, you can call me Tim. I'm a very informal person, so hopefully I can tell you a little bit of a story about some of the things I work on in my research group. As Professor Zhang mentioned, I'm a faculty member at UC Irvine. I didn't know where that was until I applied for a job, so I'm going to let you know. So if you know where LA is, we're just a little bit south. And actually, if you look on a map, there's a big blob of urban sprawl. We're part of that blob. We're just in the bottom part of it. On the right here, I have a picture of looking out. So this is our campus right here. These are the loose boundaries. This is Newport Beach, and this is Catalina Island. So if any of those things mean something to you, it maybe might orient you where we are. So my work, I think a lot about nanostructured materials, but primarily because they have a lot of defects. And I think about how we can engineer and manipulate these defects to change our properties. I'm going to start with a big picture view of how I like to think about problems. I sometimes describe myself as a metallurgist and have given some thought to what this means and the sort of pathway through which a metallurgist thinks about problems. And the basic idea is shown here. So first, we might go and understand a fundamental defect in its behavior. In this case, it could be something like dislocations control plasticity. We take that and then we try to think about how microstructure affects that mechanism. As a specific example, maybe it's, well, we know dislocations control plasticity. We can think about how precipitates can act as obstacles. But we don't just stop there. We often go back and revisit our processing and fabrication so we can use that to make a better material. In this case, if you know that precipitates are obstacles, you might go and make some alloy with nanoscale precipitation to get sort of extreme strength for whatever material you're interested in. The other thing I want to sort of emphasize here is that this process is iterative. You move around, you keep rethinking these things. In the area of nanostructured materials that I work in, we started thinking about how dislocations and other defects carry plasticity on a traditional sense. But as you get to really small grain sizes, things change. So the way these defects move, the way they interact with each other starts to evolve. It's not the end of the world. You learn something about it, you move on, and you start to sort of be creative in how you make better materials. And I really try to, in my research, try to use this metallurgy and mechanics mindset to understand different types of material problems. My home base is really structural materials. I think a lot about mechanical behavior of materials, things where we're going to make planes, bridges, components, engineering components, things like that. We do a little bit of work in energy and biomaterials as well. But it's all going through that idea of thinking about basics of defects, how they work, and how we can use that to make a better material. One thing I is also a little bit unique about my research group is that you'll often run into people who, this person might be a transmission electron microscopy person. That's their main tool. Or they're a density functional theory, first principles modeling person. That's their main thing, and they find problems that they can address. My group is very much not that. We're sort of driven by the problems. And we have this mindset that we will go and learn new techniques. So when I was a student and was training, I was trained almost exclusively experimentalist. I did a lot of transmission electron microscopy. I did a lot of small scale mechanical testing. I did a lot of depositing thin films and making different microstructures. At the end of my PhD, I was really interested in atomic scale modeling. My last paper, my PhD was from that. And now my group is roughly 50-50 experiments and computational stuff. There's no reason that I enforce that 50-50. It's just that we go after what lets us solve problems the best way. And I've given a bunch of examples here. I'll maybe just pick one up here. In this case, we were looking at how we could use mechanical deformation to change the grain boundary network in these nanocrystalline materials. And we had to pick different pieces from different types of techniques. So on the left here, we wanted to get something like these orientation imaging maps from really small nanocrystals, so only a few nanometers, maybe 10 nanometers across. And at the time, there was a way to do this. But I was a new assistant professor, and it required you to buy a piece of equipment that goes inside the electron microscope that costs $400,000, and I couldn't do it. So we looked out in the world, talked to colleagues, and found that there was a way to do this with the existing equipment inside of a scanning electron microscope, basically the same way you do electron backscattered diffraction. And we could change the orientation of how we held our sample. We could use the same principles and do this for $200. So we had to make a little piece to hold the sample. So we were pushing a little bit of new techniques experimentally. On the right side, we were at the same time using atomistic modeling to study some of these polycrystalline materials and be able to track features that we would never be able to keep track of experimentally. So we could go in this three-dimensional volume and find all these details about individual boundaries and how they changed and shifted as we had plastic deformation. We can't do that from experiments. This complements it. And then even a lot of times we tend to think about the theory. In this case, we were trying to think of and understand the best ways to describe these grain boundary networks. And we were using something called twin-related domains. So in this region, all these crystals connect to one another through a simple twinning operation. So the reason this matters is that it turns out this is really important for things like corrosion. So we were thinking about how we describe those microstructures as well. So another nice thing about being a professor is you get a chance to work with a lot of awesome students and postdocs. I put up the whole team of people up here. Today I'm going to talk about a problem in trying to make nanocrystalline materials tougher. And I primarily will be talking about work from Pulkit and Esther, who are current postdoc and PhD student in my group, as well as some work from Tianzhao and Jen, who were recent postdoc and PhD student in my group. Okay, so diving into the problem that I want to talk about and the story I want to tell you. We work with nanocrystalline materials, and the reason is these materials have very high strengths. But a downside is that high strength often comes with a relatively brittle mechanical response and microstructures which are very unstable. You can see this on this top left plot. This is a stress strain curve, a really old one of the first ones from nanocrystalline palladium and microcrystalline palladium. And here you can see your strength has gone from 40 megapascals to a little under 200. So you get a huge increase in your strength, a 5x increase in your strength. But the sample fails much earlier. Rather than elongating out and stretching quite a bit, you fail early in this tensile type of deformation. And you can see evidence of that when you look at fracture surfaces. So typically when we pull on a metal, we get this long cup and cone failure where you can see the material stretching like Play-Doh at the surface. In this case, some of the early nanocrystalline copper, they were seeing these very brittle fracture type of surfaces. This also comes up in the ability of having a stable microstructure. So this is another example from what was once nanocrystalline palladium, so this similar material as this. These people deposited these nanocrystalline films. They were getting the properties they wanted. Great, they were celebrating. But if you just leave this material at room temperature for 2 months, you go back and look at the microstructure, you now find that these crystals are now much, much bigger, tens of microns. It's no longer nanocrystalline. You totally lost that thing you were after, right? This is kind of a toy example. That's an example of a situation where you really don't have stability. But we need to really increase this property if we want to make bulk nanostructure materials. I've mentioned a few times depositing films. People also make these in little powders. These are fine starting structures, but often we want to consolidate or build these things up so that we can have a big piece of material that's made out of this nanocrystalline material. And often that requires things like using high temperatures and high pressures to consolidate these things into bigger pieces. So your material needs to be able to survive that extreme environment there as well. So the goals here are, if we want to do is address these two issues. We need to think about improving the damage tolerance of the grain boundaries, so we can get rid of that brittleness problem, but also stabilizing those grain boundaries against high temperature. And the pathway we've been going down is that if both of these properties come from the grain boundaries, let's think about changing the grain boundary structure. So the structure of those interfaces between those crystals. Luckily, there's been a lot of work in this area. I'm going to show you an example from work people have been doing to try to stabilize nanocrystalline grains. And a key idea that came up there was, rather than just think of your internal microstructure as details that we don't care about and everything is the bulk, people have been thinking about how you can describe the thermodynamics of inside the crystal and also the grain boundary region as separate entities. And if you do something like this, you can go and say, if you wanted to stabilize nanocrystalline tungsten, go and understand how you can add titanium and make a stable nanocrystalline structure. In terms of that alloy design, that's kind of nice. It's just thinking about dropping the grain boundary energy. But when you do that and you dope those grain boundaries, you also tend to change their structure as well. This is a really simple example. These people were doing a computational study, start with 2 grains smushed together, 1 grain boundary. As you add more and more, this is silver being added to the grain boundary. You see that the grain boundary excess goes up, but at some point you get this jump in this curve, and then you follow a different slope. That discontinuity there is when you have a change in the structure from these 2 types of features. So this concept here is that if you start to add in secondary elements, they go to the boundary, they reduce the energy, you can also tune the grain boundary structure as well. This is a really subtle example, but there's sort of more dramatic examples you can go after that I'll talk about in a second. So I wanted to take a step back and think about how grain boundary structure might affect mechanical behavior. And I'm going to start by talking for a second about how we make these materials. We often either smash them together, put a lot of mechanical energy into them, or deposit them very quickly so they get stuck in these small crystals. And when we do that, we often have extra disorder at the grain boundary. What's shown here on these topics, so this top one is a micrograph of a grain boundary along this middle plane in a nanocrystalline copper. And it's compared against, on the bottom here, this is the sort of perfect ideal textbook solution of where I would need to have grain boundary dislocations. The main point is that the real material has extra dislocations. So this black dislocation marker is not found in the ideal solution. So the real material has extra disorder in the grain boundary. If you prefer a computational example, you can think about this. If I take 2 crystals, tilt them to whatever misorientation I want, and put them together, that's one way to make a grain boundary. But I can also move those crystals with respect to each other, maybe even add and remove some atoms along that plane to get the lowest energy structure. If you just smash them together in some random orientation, you're going to have a higher energy, more disordered feature than if you find the low energy configuration. This is nice because it's something you can test and poke at relatively easily. So, sorry, wrong way. We started doing this. We made electrodeposited nickel tungsten. This is in the as deposited state. We could go and test what our baseline mechanical properties are, make little micropillars, get stress strain curves. Our strength is about 2.5 gigapascals, and we can see how much we can load it up before it starts to fail. What's nice is this extra disorder is relatively easy to get rid of. All you have to do is anneal your sample at a really low temperature and let it sit there for a while. You don't want to coarsen the grains. You just want to get rid of these extra defects here. So if you go and do that, you can relax the structure and then repeat these experiments and go and do a microcompression type of experiment. And here you see that your material is much stronger. Now it's well over 3 gigapascals in strength, but these samples were failing much earlier. Okay, they were experiencing the shear bending much earlier. There's other ways you can think about this. So when we're going and relaxing those samples, we're making the grain boundary structure more ordered. You can also do this with chemistry. So in this example of nickel bismuth, if you dope with bismuth, it goes to the grain boundaries. It forms a very ordered segregation pattern. These bonds are stretched and they're just ready to break. Okay? So what we learned here is that more ordered is bad. So I made things worse. But that's not the end of the world because I learned something from it, right? I didn't make it better, but I learned something. I learned that order is bad. So what did I do? Went the other way next, right? So if order is bad, disorder should be good. And you can start to think about how you can add in more of that. As an example of why this might work, is people have studied these relatively artificial microstructures where you deposit a nanocrystalline layer, then a amorphous layer made with solid state amorphization, then a nanocrystalline amorphous. And what people have found is that this more disordered layer type of structure can be stronger and more ductile. Okay? So this is our hypothesis, this idea that disordered boundaries can actually be a good thing and are going to delay our failure. I said we wanted to look at mechanisms. One way we could start to poke at this is by modeling what this process would look like. This looks funky, but it is a good way of emphasizing what we can do with atomistic modeling that can complement what we then will do actually making materials. In this case, I made a really simple type of model. I have 2 grains, so there's grain boundaries here and there in between. And in the middle of that inner grain, I'm going to operate a dislocation source. I'm going to kick dislocations in either direction. The reason is that people have seen that dislocations being absorbed at the grain boundary is probably the explanation for why we have that brittle behavior in nanocrystalline materials. So we can do something like that, kick dislocations in either direction, get them absorbed here, but then change what the grain boundary looks like. Sometimes we can have ordered grain boundaries, or we can put in amorphous regions and things like that. This is a few years old, so I'm not going to spend a lot of time on it, but I just want to show on the top is an ordered boundary, on the bottom is an amorphous grain boundary. When you have an ordered boundary, you get these red regions, which are high strain regions, so that dislocation is absorbed and accommodated, but it's in a relatively thin region at that boundary. Whereas in the amorphous region, you have this thick region that can co-deform and sort of accommodate that stress over a larger volume. The thing that matters in terms of properties is you can go and look at the number of dislocations you can absorb before a crack forms and see that it's a function of the thickness of that amorphous intergranular film. So if you add an amorphous intergranular film and keep making it thicker and thicker, you can absorb more and more dislocations. Bringing this back to properties, it means you can survive higher strains. This is just showing sort of why that might matter. Another nice example, this is from Eric Bitzek's group. They were looking and trying to isolate this dislocation absorption event. They added a dislocation artificially, strained it, let it go and be absorbed, and we're finding these high stress regions at the boundary, which is where cracks were going to form. What we're more interested in is how we can then go and add disorder to the boundary. And we've been using a relatively new term in our field. This is called grain boundary complexions. But the idea is that if you dope grain boundaries, you can actually go and access different thermodynamically stable phase-like structures at the grain boundaries. So this is showing going from left to right. This is sort of what you would call a clean grain boundary. This would encompass all the different ways you could put together just crystals in a pure metal to make a grain boundary. You can have different types of segregation patterns at the interface. And you can also have discrete nanolayers, so films that are a few nanometers thick at the grain boundaries. Another way to think about this is as you go from left to right, you're having increasing structural disorder. Okay? So this type of thing would be what we are really after. And people have developed really nice thermodynamic descriptions of what's happening here. We don't need to dig into it too much because we're just going to go and apply this and make materials with this. But the basic idea is you need to think about the energetics of going from a single grain boundary with an energetic penalty to now 2 crystalline amorphous interfaces and then some amorphous region at the surface. And when this right type of configuration has a lower energy than the left, that's when you're going to form these amorphous grain boundaries. And this is just an example of somebody going and finding one of those that's a little over a nanometer thick. So I'm going to sort of show you how we can apply these types of principles and make better nanocrystalline materials. First, I'm going to attempt to relatively rapidly test this hypothesis in copper zirconium alloys. And we're going to look at thermal stability, deformation, and radiation. And then I'm going to show you how, spoiler alert, this works. I'm going to show you how we can take that idea and then apply it to different materials and broaden the reach of this type of idea. Okay, so when we first started working on this, we said we wanted to make a material that could have an amorphous grain boundary. And copper zirconium is the best example of a binary glass former. This is the first material people made into a bulk metallic glass with a simple composition. So what we did is we said, let's take that sample. We're going to choose some composition where we've added enough zirconium that it will need to segregate out to the boundaries. And then we're going to heat it up very high temperature, but keep it in the range of what should still be a solid on the phase diagram. So when we do this, we get segregation of zirconium to the boundaries, and hopefully we also get a pre-melting type of behavior. So we get that formation of that amorphous complexion. We can test this by quenching down fast and then going and doing TEM. And sure enough, we find those amorphous grain boundaries in the sample. So here, crystal 1, crystal 2, an amorphous region was featureless in this FFT. The reason this is nice is that we can go and redo that same experiment. So heat it up, allow for segregation and pre-melting. But the whole concept here is that this amorphous grain boundary is a high temperature structure, and we had to freeze it in. So we can just do that cooling step a little bit different, and rather than quickly cooling it, slowly cool it down. So the same thermal history, same grain size, you still have zirconium at the boundaries, but when we go and do the TEM, we never find these amorphous films. We only see these boring ordered grain boundaries. So grain 1, grain 2, relatively ordered grain boundary there. And what that does is that gives us two materials that are the same in every way except for their grain boundary structure. We can go and see how that helps our processing. So, for example, we make these materials with mechanical ball milling that gets the grain sizes really small. We can go see if this helps our stability of our microstructure. If we measure grain size as we heat up, we see that we only have a small amount of grain growth until we hit the melting temperature. Okay, so we're relatively stable grain size. And this is actually nice because it lets us go and make bulk materials. So these things are, we make them in my lab, they're chunks this big. And we can go and study the processing. I'm less interested in talking too much about that today. But the basic idea is this marked area right here is where we start to get those amorphous complexions. The gray area is sort of from experiments. The purple one is from theory, but they're showing us that that's where we start to get amorphous grain boundaries. And that's where we get a big jump in our density of these samples that are pressed, but our grain size still stays relatively small, and we can make 100% density materials with about grain size of 50 nanometers. Because we're interested in mechanical properties, I want to jump in and look at some mechanical testing. We've done lots of different types of tests. I just want to show you these in situ SEM tension tests we've done. In this case, we can either do it on a bulk sample or even on a small particle of this material. We go and we make something that looks like these micro compression pillars, but then we also mill around and leave a little gauge or a little grip section at the top so that we can pull on this. We test these with this Femto Tools system. It's basically a little micro manipulator that goes inside of the SEM. But what's nice is we can machine the silicon tip into whatever shape we want. In this case, we come down, go in front of that thing, hook it, and pull it up and deform it. So I'm going to show you some movies real quickly. On the top is the copper zirconium sample with ordered grain boundaries, and on the bottom is the one with amorphous complexions. Again, everything else is the same. When you start to pull on this, you fail rather abruptly here, whereas you stretch and pull out for the sample with amorphous complexions. You can pull out these images and see much more clearly. There's almost no global plastic or local plastic strain here. You get lots of plasticity here when you have amorphous complexions. And then we could go and do things like measure the ductility in terms of area reduction and see that we've had an increase of about 2x by adding those amorphous complexions. With these little in situ experiments, we can also do fun things like look at how plastic strain is distributed to the gauge section. In this case, we put little platinum markers on the surface, and then we could basically track how the individual regions are elongating. And here we're going to have comparison of 4 different samples, 2 with ordered boundaries, 2 with amorphous boundaries. And here we can plot, this is a color plot, and then here is the sort of quantitative data. But for the point is, for the sample with the ordered grain boundaries, you get very localized strain. So once you start to plastically deform, localizes and the sample breaks. And we can compare that with the sample with the amorphous complexions. We have much more distributed plasticity, and we can get a more homogeneous deformation. We should think for a second about this, because one thing I'm telling you is that I'm adding an amorphous metal to my grain boundaries, which by itself is not a very ductile material, and that makes my material more ductile. It seems a little bit counterintuitive. But you can find other examples on the other side of this continuum. So I'm saying that adding some fraction of amorphous complexions is good. People have shown that if you're looking at amorphous materials, adding some small fraction of nanocrystals can be good. So in this case, you go from, this is a pure or a regular amorphous material where it's homogeneous microstructure and it just shear bands. If you add in the nanocrystals, you can get much more plasticity there. The point here is that in this case, one shear band goes across the whole sample. When you add in all these nanocrystals, you get a bunch of tiny shear bands. So we're not changing that dislocations are moving around and being absorbed. We're just making it more tolerant to absorb those dislocations. You can even see examples of this in the metallic glass one from really beautiful in situ experiments that people have done recently. Here they have a deposited amorphous material with little tiny nanocrystals inside the material. And what these people were doing is pulling on this and showing that the shear band deflects around that particle. The main point here is that the flow mechanism or the plasticity mechanism is not always the failure mechanism. So we're able to delay premature crack nucleation. And in this side, they're able to avoid catastrophic shear banding. But in both cases, that's okay. You're going after what's that failure mechanism, not just what starts to move plasticity. So if you've made tougher grain boundaries, you can also think for a second about how you can use this damage tolerance in other ways. I just want to show you a slide or two on if materials are resistant to mechanical damage, they can also sometimes be resistant to radiation damage. This is an example here of people using energetic ions to bombard a material, and look how much damage builds up. And by having a nanocrystalline material with lots of interfaces, you can get less damage. So these can be sinks for that damage. We've studied this in the context of these amorphous grain boundaries and seen that we get much less damage compared to ordered materials or single crystals. We collaborated with our friends at Sandia National Lab. My student Jen actually went and spent some time there. While she was there, they made her do like a photo shoot. I like to show this and always like kind of embarrass her a little bit. Although I will say the first time I showed this to embarrass her, I was wearing this same shirt, and somehow it was more embarrassing to me. I don't know, it was like an Old Navy shirt or something that I was wearing too. I also love this picture because I always wonder what he's doing. I don't know, he's back there, he looks very serious. Anyways, what's kind of cool is they can build up charged ions and bombard your material, but what's extra cool is they can do it and have this happen inside of the transmission electron microscope. So Khalid Attar, who's now at University of Tennessee, built this microscope that from the front looks very much like a traditional TEM. But from the back, you can have the charged ion beam come in and be hitting your material and watching what's happening. So we can take this same nanocrystalline copper zirconium and bombard your material with energetic ions. When you're seeing changes in the contrast, it's not necessarily that you're seeing the charged ion, you're seeing the effect of that charged ion. So it creates defects. Sometimes these coalesce into dislocation loops and things like that. To first order, you can go and look at how stable your microstructure is against this irradiation. For the samples with ordered boundaries, we see both changes in grain shape, but also changes in grain size. So this is an example where you see some modest changes in the shape, but here you see this grain has grown quite a bit after we damage it a little bit. And even just on the surface, if you look at the amorphous complexion examples, we see the absence of grain growth. We only see changes in the grain shape. So the microstructure is more stable. More interesting is how that damage builds up inside of the material. So because these are done in situ, we can keep track of where we are in time. connect this. This is displacements per atom, a sort of measure of how much you've bombarded your material, and look at individual grains and say, okay, how much defect content do I have in there? And make a plot like this. So this is the defect cluster area as a function of dose. And what you'll see is that the sample with the amorphous complexions is below the one with ordered grain boundaries. So that's a good sign. It means we're damage resistant. And more importantly, is this sort of change in the slope. So the damage is building up much, much more slowly in these materials. And you can test this by going and doing an ex situ type of experiment where you really bombard it. In our case, we went up to about 200 dPa, and you really see the difference between these damage states. Okay, so hopefully I convinced you. We can make materials that are tougher. We can make materials that are more resistant to radiation damage. But is this just some weird, quirky example of copper zirconium? This material you chose happens to work and it's not applicable to other things. By the way, there's plenty of examples out there in material science where people got something to work, wrote a Nature paper on it, and then nobody else ever made anything out of it. So we're trying to avoid that. And we want to think about how we can go and use this more broadly. So we thought about what was really happening and how can you promote these disordered grain boundary transitions. And we started to think about what would really have to happen. Well, so the first starting requirement is you need to have segregation to the grain boundaries. So I said I want to add in alloying elements. I want them to go to the grain boundaries and change the structure. You got to have something that goes to the grain boundaries. If that's not true, then the idea falls apart. We don't have to do the hard work there because I mentioned early on that people have been studying which alloys can be thermodynamically stable. So for example, this is some work from Chris Shu's group where they went and said for any type of solvent, so let's say you want to use aluminum, which materials could you choose that would segregate to the grain boundary? And you can solve that. Okay, so we have a place to start there. The difference in our work is that we basically need to have segregation, but then for that grain boundary region to be a good glass former. All right? Again, people have studied this separately, so you can start to look at what has generally worked. So the rules for what makes a good metallic glass are you usually need 3 or more elements, you need large atomic size differences between the elements you're putting in, and you need negative enthalpies of mixing. So we're going to start poking at this and see if this combined type of set of rules works well for choosing materials. As good scientists, you notice there's lots of things here and you want to decouple them. So we're going to first start by restricting ourselves to binary alloys. So which means we're going to forget this for a second. We'll come back to it in a little bit and just look at these two features. So I'm going to show you, we went and made nanocrystalline copper alloys, copper zirconium and copper hafnium, copper niobium and copper moly. And the idea was that if you look at these rules, you would predict that these top 2 would form amorphous grain boundaries, and these bottom 2 would not. Okay. We also wanted to see if this idea that we were studying in these mechanically alloyed materials was possible with other types of processing routes. So these were sputtered. We annealed at a lower temperature to allow for segregation. And then our idea was that if you have segregation, that local transformation at the boundary shouldn't take very long. So we do a really high temperature annealing, but only for a short period, only 1 minute. And we can go in, I already showed you copper zirconium has these features. We showed it for the sputtered films, but I'm not going to show it here. You see these big, thick amorphous grain boundaries in copper hafnium, and then in copper niobium and copper moly, you always get these boring ordered grain boundaries. So crystal 1 and crystal 2 are coming right up against each other. So that set of rules starts to work. We're able to see that we need to have segregation. We need to have a negative enthalpy of mixing, and a large atomic size mismatch works. We could ask ourselves if we need to do both. We weren't able to really test this with our own experiments, but we were able to more easily go back and look at the literature and find evidence to address this. So people didn't realize it at the time, but as we start to build this idea of what the ordered and disordered grain boundaries do, we could find that grain boundary embrittlement is typically related to ordered grain boundary structure and activated sintering. So when I showed the density versus temperature curves, that big jump in density of a consolidated sample is related to these amorphous intergranular films. So we could go and look at a bunch of data in the literature and, for example, find that in some of these tungsten alloys, There's materials which have a negative enthalpy of mixing, but only a small atomic size mismatch. So we're able to sort of go through and refine our understanding. So the absolute requirements, we need to have segregating dopants. We need to have a negative enthalpy of mixing. And then these other ones so far are optional, but we think they're helpful. I'm going to test this, but right now we don't think we have to have these, but these large lattice, constant, and 3 or more elements are optional but helpful. Okay. But with that idea of segregation and negative enthalpy of mixing, we can go and make our own plot for what should work. So for example, we can go and make something that, if this is your base material, what would you want to add to create amorphous grain boundaries? Anything that's an X here means that it doesn't segregate. So it doesn't reach that, it doesn't match that first criteria, that's not good. And then we want things that are blue, preferably dark blue here. So for example, I could say nickel, what works? Nickel zirconium works. Let's go and redo that same experiment. Hey, we found amorphous grain boundaries in nickel now, okay? You can even go and see how we can revisit other types of materials that people have studied to death but didn't see these features. So nickel tungsten, our alloy selection rules suggest would be able to form these amorphous grain boundaries, but people had never seen them before. I actually did my PhD all on this nickel tungsten system. This is the type of data you historically have seen. So the grain size versus annealing temperature. It stays stable until at some point it grows and goes away. Okay? Now, when we look at our predictions, we predict that amorphous grain boundaries should form up here. So we actually went and took this material, annealed it at these higher temperatures, looked at the grain boundaries, and we find examples of amorphous grain boundaries. They're not super thick. They're only about a nanometer, maybe a nanometer and a half, but you do see those amorphous grain boundaries. And the reason this matters is if you go back and add this high temperature data to this type of curve, you actually find that your grain structure is more stable at 1,000 degrees C than it is at 900, which is a very counterintuitive type of thing. You tend to think as you increase the temperature, your grain size will grow and coarsen. It's more sort of extreme type of conditions. So this, you sort of can see the evidence of a new stabilization regime. Okay, I'm running out of time, so I'm going to, oh no, I'm not running out of time, never mind, I still have a little bit. So we can start to test those other things. So I mentioned that these first two are required, you have to have them. We can start to see how these other two can affect things. So first I want to show you what happens when we add in 3 or more elements to the grain boundary. So I'll make a ternary alloy, copper, zirconium, hafnium. I'll make a quinary alloy, copper, zirconium, hafnium, niobium, titanium. Now this, you've probably seen things like this with things like high entropy alloys, where people are mixing things in. I do want to sort of clarify, this is not really that. This is something where we have 92% copper, 2% of the other things. So it's still primarily copper. The reason I'm showing this data is only that, so in the copper, zirconium, hafnium, you get grain boundary segregation of the two. Even though I added in 4 doping elements here, it's important to double check yourself. Are these things all going to the grain boundary in the way I wanted to? This is a good example. So you see the copper depletes at the grain boundary, niobium goes up, titanium goes up, zirconium goes up. I don't see anything with the hafnium, okay? What actually happened in this case was the hafnium all got trapped as carbides inside of the microstructure, okay? So what it really means is we have examples of 2 binary element alloys. We have a 3-element alloy and something with 4 elements at the grain boundary. But what you can do is then go and see if you have amorphous complexions, but more importantly, go and measure the distribution of the thicknesses of those amorphous complexions. So we go in and we measure about 50 of those amorphous grain boundaries, measure the thickness, and we make a plot like this. So this black plot is what our binary copper zirconium looked like. Most of the amorphous grain boundaries are, between 0.5 and 2 nanometers thick. There are a few that are thicker. And as we go from 2 elements at the grain boundary to 3 to 4, we're pushing out to the right, which means we're getting thicker and thicker amorphous grain boundary complexions. So increasing that chemical complexity does tend to increase that complexion thickness. And remember, increasing complexion thickness means I can sustain higher strains and more dislocation. So there's a reason I care about that. It's not just thickness is higher. No, it's better properties. We've recently been looking at a system that actually checks all of these boxes. So it's something that also has large atomic size differences between all of the atoms. It's actually relatively hard to find things that can address all of that. But in this example, it's an aluminum-rich system where we're putting in some transition metals and magnesium, and then a rare earth metal, yttrium. We can go and find that we can make big bulk pieces of these nanocrystalline aluminum with grain sizes that are about 50 nanometers. So that's a good sign. But more importantly, what's really cool is, so these are images of amorphous complexions in that sample. But in all the other things I've shown you till now, we did something where we heated it up to high temperature and then rapidly quenched it down. We made these bulk samples in a hot press, turned off the hot press, and waited a few hours while it cooled down. These are not quenched at all. These are cooled over multiple hours, and they still have those amorphous intergranular foam. So they're very, very stable in these microstructures. If you actually go in, this is just showing other examples. All of these ternary alloys have these amorphous grain boundaries. If you redo this experiment where you heat it up and then quench it, you get extremely thick amorphous grain boundaries. So these are about 9 nanometers thick, right? The other thing that's pretty cool is that we're starting to see in this aluminum system that these amorphous grain boundaries can be nucleation sites for other types of features inside of our material. So we actually form these nanorod carbides that grow out of the amorphous intergranular films. So whenever you make these materials, you always have impurities, carbon, oxygen, things like that in. In this aluminum system, these aluminum carbides want to form, and they nucleate here and grow out and actually increase the strength of our material. Here we're showing chemistry, here we're showing structure. You can see that carbide structure. When these things are really small, they actually have a disordered structure themselves, kind of like the amorphous grain boundary that they were born at. But as they grow inside of your material, they become crystalline, and you can start to see them take up more and more of the microstructure. There's a lot of details here, but all we're basically looking at is some of the things we add, like nickel and yttrium, which segregate to the grain boundaries, also segregate to interfaces along these carbides that grow in our material. But getting to the punchline, you end up getting some of the strongest aluminum you can find. So here is showing some preliminary data on hardness. So we're harder than many of the other nanocrystalline comparisons. But we can also do mechanical testing. Here we're starting with micropillar compression. So the aluminum magnesium yttrium alloy has a strength approaching 1 gigapascal, which for aluminum is pretty crazy. And to put that into sort of reference that we might understand, so these marks here in gray are what you would get for the yield and ultimate tensile strength of 775 T651 aluminum, which is the strongest aluminum you can buy sort of from industrially off the shelf right now. So we're getting multiple hundreds of megapascals higher in the strength. There are some interesting complications. Sometimes in these micropillars, when you do the compression, you can get a shear banding type of deformation. We've actually studied this and found that it has to do with the distribution of some secondary intermetallics you get inside of your material. And if you don't have a pathway that's free of those intermetallics, you can have the development of shear band, which coarsens your microstructure and destroys it. Because we can make these things in bulk, we can also do things like bulk compression experiments. These are, again, pieces that are, hold them in your hand and see the same thing. So you get high strength, reasonable plasticity from materials in their bulk form. One thing that we're not able to do very well is play with the composition of these materials. So the way I make these materials is we ball mill powders, compress them into pieces. If I want to change the composition, I need to go back to the beginning, add in powders in different ways. It's relatively slow and laborious. So we've been collaborating with a good friend of mine, Dan Gianola at UC Santa Barbara. He does this really nice combinatorial sputtering type of technique. So he can go through and on one silicon wafer go and make dozens of different compositions in a certain alloy space. In this case, I'm showing the aluminum nickel yttrium. And he's doing relatively quick experiments, measuring things like hardness and grain size and lattice parameter as a function of annealing temperature. But the reason he's doing this is he can then go and get some data that he can put on the sort of ternary phase diagram, and for example, find that your transition temperature, so where you start to get evolution of the microstructure, is higher, which is what you want, near 1-to-1 than it is 5-to-1. So he's able to go through and basically tell us how much nickel to yttrium ratio do we want to go and have. Okay, so with that, I want to leave you with some open scientific questions we have. So one thing we're digging into now that's really exciting is these amorphous regions at the grain boundary are quite interesting because they actually interact with the crystalline material next to it. So this is a model of a bulk metallic glass. It's primarily composed of these disordered types of packing structures. The interior of an amorphous grain boundary looks like that, but this region at the edge where it starts to hit the crystal looks very different and has a much higher density of these ordered packing motifs. And it turns out that that's really important because this is where things like dislocations are coming in and being absorbed, or those point defects from the irradiation need to be accommodated and brought into this bulk material. So we're looking both at these structures, but also how variations in those structures affect the damage tolerance. And I'm not going to show the data, but relatively subtle changes in the the density of those ordered packings can give you things like a 2 or 3x increase in your damage tolerance of your grain boundary. And we also are trying to poke at how we can control that in a meaningful way. And one way we're trying to do it is by looking at how you get interesting patterning of different elements at the grain boundary. So this is showing a grain boundary in copper, zirconium, niobium, titanium. I said all those things go to the grain boundary, but it turns out they don't all go to the grain boundary evenly. So this interior region, which is more disordered, ends up being more heavily doped with zirconium. It's always hard to see with lights and things, but these regions here are marking those amorphous crystalline interfaces, and they're more heavily doped with niobium and titanium. So we think this is actually connected to the local environments that these elements like to be in. If I go and I study copper niobium by itself, it forms an ordered segregation pattern. So it kind of makes sense that the niobium likes to be in these ordered packing motifs. But we think we can tune this and control it to be able to engineer these sort of local short-range order patterns and tune these responses. Okay, so I want to leave you with some take-home points. Hopefully I showed you that amorphous grain boundary complexions can improve thermal stability, ductility, and radiation tolerance of nanocrystalline materials. If you're thoughtful about how you understand how these things happen, you can come up with alloy design rules. In this case, we were looking at stabilizing an amorphous structure at the grain boundary. And then you can use these to make different types of materials. Again, the idea is, so we've made copper, nickel, aluminum. I was just on a phone call yesterday with somebody. We're trying to extend this to steels. There's different reasons you would want to extend it to different materials, but the idea is whatever materials concept you come up with, if you're really thoughtful about how you understand it, you can make sure that it has a broad impact. All right, thank you very much for your attention. Love to answer any questions you have.
You said that at some material mixtures, you're able to produce different thickness of amorphous layers. Mm-hmm. Have you noticed that there's any diminishing returns depending on the thickness of the amorphous layers? So
there would be if you go to the extreme. So if you were to make it 50 nanometers thick, you would end up having a material which is mostly amorphous material, and it probably would be pretty brittle. So until now, we've been working in the range of 1 to, I would say, the average even in the aluminum is 5 nanometers, with some outliers that are 9 nanometers thick. In that range, you're still getting a benefit from increasing the thickness of the amorphous films. So you certainly would run into it if you kept going. I'm not sure you can get much thicker than that and have those stable films. So within that range of a few nanometers, thicker is better.
question?
You said 100% density. Does that just mean that the particle is fully occupied in space?
Yeah, so these are loose powders, like you blow them and they would fly around when you make them. There's all kinds of tricks people do for this sometimes. We just hot press it. So pressure and a little bit of temperature, and you get a sample that doesn't have pores, basically. That's what we're going for. Which I didn't spend a lot of time on, but that is a pain in the butt when you're doing material processing. So often you get a bunch of porosity and things like that, and you're fighting that, and yeah.
So I have a quick question about the thickness of the amorphous layer.
Yeah.
So have you, like when you add more, like just for example, the copper zirconium, you add more zirconium, will the thickness get thicker or?
There is, so there definitely will be a composition effect here. We haven't studied that yet because we've been doing it in these random polycrystals in these ball mill samples. So the reason is, when you do that, you end up getting a lot of different types of grain boundaries with different local compositions. We are just starting a project where we're going to study this and also the effect of adding the higher complexities. But the way we're going to do this is we're going to deposit these layers and make them in a little bit more controlled grain boundary composition at a grain boundary we know it's there, then heat it up to close to the melting point. And then in that case you're able to compare apples to apples. So it's a good question. I don't have the answer for you right now, but in a few months maybe I will be able to tell you, right? It certainly will. There will be a optimal grain boundary composition for forming the glass. That's true.
Yeah, I have a quick question.
Yeah.
So, do you think the state of this amorphous grain boundary will matter or not? For example, initially I designed to tolerate dislocation very well, absorption very well. But with the time run, with the loading going on, and that capability is degrading or is losing. Initially, it can absorb. But
Sure.
With the plastic deformation going on.
Well, yeah, because you do eventually overcome its ability to absorb more, so it will fail at some point.
Yeah.
What we're actually kind of excited about, and probably more on the radiation side, is that you should be able to, just like you can with glasses, you should be able to rejuvenate that structure. So if you absorb a bunch of dislocations and change the structure over time, you could take it out of service, heat it back up to near the melting point,
Yes.
quench it down,
Recover.
and it would recover that
Yes.
structure.
Yes.
So I think you could do that.
Yes.
Now we're making thought experiments and stuff. I haven't tested that, but I think it should be possible.
Yeah, water recovering is exactly what I'm thinking.
Yeah, absolutely.
With the time going on, I want to recover the capability.
I think you should be able to, again, rejuvenate is what they call it in the glass area, but yeah, certainly I think you should be able to get back to that starting structure.
Okay. Yeah, makes sense. Yeah. Any more questions? If not, let's.
Great. Thank you very much. Thanks.
I have some modeling stuff related with this, with the time going on.
Yeah,
with the
for sure.
going
Yeah.
on. I want to characterize what is the change of the state.
I think that's a really important question.
Yeah, because I want to fingerprint it. Yeah, and then recover.
Hey, Mohammed.
Hello.
Yeah, I really enjoyed your talk.
Thank you very much.
So we're gonna meet at
Yes.
11:30.
Sounds great.
Yeah, we'll have a good time. So what's he gonna do for half an hour?
Half an hour, just show him around.
Yeah.
Okay, okay. And
Do you want me to do it?
no, 11:30 is good, but I guess they forgot to bring the coffee and stuff.
Yeah.
But you can take it for
Yeah, perfect. Yeah.
I'll never say no to a call.
Yeah.
Sounds great.
Yeah.
I will bring him.
Okay, I'll catch up with you.
Hey,
I didn't quite get the last part of your website.
We'll talk some more.
EDU.
I wanted to make sure.
Right on. Yeah. Thank you. Thanks. Let me just shut down real quick.
Even for the same amorphous grain boundary, without loading, does that differ with each other? Same misortation angle, same composition, the state, does that change when you use different processing process?
Oh, I'm sure. Yeah,
It
no,
changes,
100%.
right?
Yeah.
Yeah.
So another question people sometimes ask me from the processing side, which I don't have an answer for, is
Yeah.
So I'm guessing that the ones made with mechanical alloying are actually more disordered than the ones from sputtering because you get more oxygen and carbon and things like that, right? Good glass, there's plenty of good ceramic glasses, right? That's where we started thinking about glasses. And that would be the biggest difference is you have different impurities in the ball milled ones versus the sputtered. So I'm sure you have a different grain boundary structure.
Yeah.
Excuse me.
Yes.
Yeah, your presentation reminded me of the heterostructure material.
Yeah.
So I'm wondering, have you tried to test the material in like a millimeter scale, like a micro scale size, because it may also show some good properties.
So we've done it micro size, and we've also done bulk.
Bulk, okay.
So,
like dog bone, yeah.
So I guess there's a millimeter size in between, but my take is really all of those are big enough. The other thing is like when people study things on the micro scale, they're usually like single crystals or something inside that micro pillar. Our grains are still thousands of times smaller than the micro scale pillars. So we have millions of grains. So it's basically a bulk test. Even though it's done in an electron microscope, it's a bulk test. Because when people first started doing micro pillar things, they were like thought micro was different, but it's really sample size compared to your microstructure. That's what matters. So for us, our microstructures are so fine that we can do a lot of that testing, and it seems to be it's bulk like.
Oh, I
Great.
see. Yeah. Great. Thank you.
Yeah, thanks.
Yeah, I can take you to a coffee, please.
Sure, we can also just walk around or whatever you want to do.
Around,
Yeah.
We have half an hour. What kind of a matrix do you use to characterize the state of this amorphous grain boundary? For example, for grain boundary, clean grain boundary, we have mutation angle, NH, the free volume. We have so many things to use. But for amorphous things, we use what? Use short range order or
So we've been on the modeling side using short range order. So
Short range
using
order.
like Voronoi, polyhedron, and density of those
free
things.
volume things?
Free volume works
Yeah.
pretty well.
Yeah.
I think you're right. It's
Because eventually we need this kind of sort of state variable in the continuum level.
Yes.
Develop a continuum model, right? How this
So
how this
it's
state variable will
relatively early, but we've started doing some stuff with people doing synchrotron X-ray, and they're able to see the signature of these amorphous grain boundaries in that type of experiment. And we're wondering if maybe we can get some idea of grain boundary state from that. Because I think people have done